Hi, so I will talk about AutoNAT v2. It's the second version of AutoNAT. I am Sukun. I work on GoLib P2P and I am Sukun RT everywhere. Feel free to spam me. Anyway, so yeah, just some overview about lib P2P, like very 50,000 feet overview. So lib P2P creates an overlay network for you. So you don't have to worry about addressing nodes with their IP address. And you can pretend that nodes are actually represented by their public keys. This is a tricky problem because we are essentially mapping these public keys onto the internet infrastructure, which runs primarily on IPv4 and IPv6. But the idea is that you can bring in other transports also if you want. So I know Bertie tried to run the libp2p over Bluetooth, and this is this task is difficult, and there are a lot of details which can go wrong. That's why I picked AutoNAT for this talk. It's a small enough protocol which we can analyze in reasonable detail to understand what sort of issues can occur when you go with this mapping from public keys to having an IP address which works with the rest of your OS, basically. Anyway, sure. So yeah, what is AutoNAT? So it's a very inappropriately named protocol because it has nothing to do with NATs. It's a protocol which tells a node whether it is reachable from the public internet or not. So whether you should go out and put yourself in the DHT or not, basically. Because if you are not reachable from other nodes in the network, you should not be advertising yourself everywhere. It just wastes resources for other people. I am happy to bike shed on the name. Yeah, uh, suggest on the repo specs everywhere. It's fine. Yeah. The problem with understanding your reachability is that routers do not provide you this information. The good routers do. There is a weird AWS configuration which will not provide you with any information about your external interfaces, especially if you are on IPv4. And there is a long tail of routers which will just do anything they can. Uh, and in general, it's good for a node to understand whether it's public or not. Ideally, you would like to obtain some relay reservations, and you not want to spam the DHT with addresses that you are not reachable on. So yeah, let's first look at the current version of the protocol, how we go about finding. The protocol is very simple. You just say, uh, anytime you want to understand whether you are reachable or not, you pick a random server which you are connected to, and you ask it to dial you back. And the way you ask it to dial you back is that you tell it your list of addresses, that, okay, I am available on this IP address on Quick and this IP address on TCP. And the server will try to dial you back. If the dial succeeds, it will tell you, yes, successful, yes, you are reachable. If it fails, it will tell you are not reachable. So yeah, exactly, simple protocol, but there are a lot of issues that can happen. So let's see some of them. So yeah, let's get the simplest one out of the way. Oh, okay, let's get the difficult one out of the way first. So yeah, exactly. So we would like to pretend that there is one internet. We would like to pretend that translating public keys to IP addresses is not an issue. But as it turns out, this is not the case. We uh, primarily we have two internets, IPv4 and IPv6. They're designed in such a way that they mostly do not interoperate. So there is an issue on the Kubo repo if you are interested in making IPFS Kubo work with IPv6 only nodes, and currently it does not work. Part of the reason is some of the issues with AutoNet v1. And the issue here is that if you are reachable on your IPv6 address and you ask an IPv4 node, am I reachable? It will obviously tell you no. Similarly, nodes have different connectivity based on whether they are on TCP or UDP. So if you are reachable on TCP, but the server's UDP port is blocked or UDP access is blocked, it will tell you you are not reachable. So the simple protocol that we have currently makes it difficult to have accurate understanding of whether you are reachable or not, and what exactly is your reachability. Because as we, again, reachability is not exactly a single yes or no boolean. It is actually a four tuple based on TCP, UDP, IPv4, and IPv6. This is the simpler issue, that there is no way currently to verify whether the peer actually dialed you. So a malicious peer can just tell you, yeah, you are reachable, and you have no other way to verify it. Okay, so yeah, I will come. This is a trickier issue. This is actually a currently open issue in Rust P2P. But so this is regarding how firewalls work. So in the first case, you can see here that client connects to the server on its with a quick address. The server's port is 1, the client's port is 1. But when the client connected to the server, it opened the firewall ports when it made that quick connection. Since it sent a packet out, the firewall ports are now open. Now the server, when serving an AutoNAT request, it needs to ensure that it does not dial out, it does not make the dial to the address requested by the client using the port which the client is connected to. If it does that, this protocol just does not work. This is actually an issue with a lot of current implementations out there. Golab P2P is fine. And this ties in with what Steve said initially about improving our specs. Like, we would like to get these sorts of shortcomings in the specs so that implementers have an easier time dealing with these issues. Yeah. Again, so something which seems very innocuous. So these issues that I've mentioned with the current implementation can be piece by piece patched in. Okay, you can go and fix the Rust implementation to not reuse the port. You can add a nonce to the request to ensure that the dials are successful. You can send only a single address in every AutoNAT request, which gives you reachability per address. So you will be able to say, okay, I'm reachable on web transport and not reachable on TCP. But the issue is that when we implemented AutoNAT v1, we thought it was a good idea to just make a best efforts understanding of whether the client is reachable or not. So the implementation actually currently will dial the address that you are connected with the server on. It does not matter whether you sent it in the request or not, it will always dial this address. This makes it impossible to upgrade. Yeah, so again, one of those issues where you need to be very careful when implementing or specifying a protocol which deals with this sort of stuff, that you do not want to do more than you can, sort of. Yeah. So in this particular case, the server will actually dial both the addresses. It will dial TCP, which was specified in the request, but it will also dial the quick address. So which makes it difficult to use AutoNAT v1 to determine whether you have reachability on a particular transport or not. So for AutoNAT v2, what we would like is we want to test reachability on individual addresses. This is also for a bunch of other reasons. So if your web transport address is not reachable, you would like to obtain a relay reservation with a node which has a web transport or WebRTC direct address, so that browsers can first dial that relay and then upgrade over WebRTC browser to browser to your particular node. And of course, we want a verification mechanism to verify that the server is not lying about our reachability status. So the AutoNAT v2 protocol, it is similar to the first one, but we ensure that only one dial is made so that you know exactly the transport which you can be reached on, transport IP pair. So you send the server the list of these addresses, IP4 UDP, quick, IP4 TCP, IP6 quick, with a nonce. And in this case, the server has no quick connectivity, so it will skip the quick address and it will dial the TCP address. And when it completes the dial, it will send you the nonce you sent in the request. So the client can tally the nonce on its side and it can verify whether the server is lying or not. And yeah, so this gives it accurate information about whether the server is, whether the client is reachable from the internet on TCP. What can go wrong? So in general, it's a terrible idea to allow to basically send to the server that, okay, dial this random IP address on the internet, because you will obviously target a bunch of people, right? Yeah. So we want to prevent this amplification attack, right? So you are connected to 1,000 peers, you are doing your job, you are participating nicely in the DHT or in your IPFS network or whatever. But now you decide, okay, I don't like this node. You send this target IP address to all your peers, and all the peers dial this target IP address. The peer has to waste a bunch of resources. Hopefully the resource manager will stop the attack and not take the node down, but it's still not a nice position to be in. So, and this is the list with, this is the problem with having a system where you want to verify connectivity on both IPv4 and IPv6, but you don't want to get into this idea of whether this server allows me to do IPv4, whether this server allows me to do IPv6. And for some cases, you might actually have two IPv4 addresses. Yeah. So anyway, so we have an amplification attack prevention measure. And the idea is simple-ish. The thing you need to understand here is that in this attack, where you are asking random peers to dial a target node, the cost spent by the target node is the handshake cost. And TLS handshake primarily consists of data transferred. It also spends a bunch of compute resources on the server. But if you wanted to do a TLS flood attack, it is easier for you to do a TLS flood attack without spending a lot of compute. You can just generate your keys once and use the same keys for all the TLS requests you're making, or for all the TLS client hellos you'll send, right? So yeah, we have added a prevention step where if the server sees that the client is wanting to dial a IP, we have reason to believe that it is not the client's IP. The server can ask the client to provide a large amount of data. Okay, so typical TLS handshake sizes are 10 to 20 KB. It's lesser than that, but yeah, 10 to 20 KB is good enough. So in this case, the server will ask the client to provide something like 100 KB data, which is, it's useful enough data for the client to provide if it is interested in knowing its reachability. But for an attack purposes, there is no point now doing this attack via AutoNAT, and the client can do the attack itself if it is interested. Yeah. So, okay, this is the final protocol. You send the server the list of addresses you dial on the list that it can dial. In this case, we are connected to the server on IPv4. We ask it to dial an IPv6 address. The server tells the client, okay, give me 120 KB data, I'll dial it. And the client tells the server, client provides the data to the server dials the IP address. In this case, it's a success. And yeah, so hopefully everything works. I am almost convinced of the security measure in place. If you have issues with, or if you think this is not a good enough solution, please comment on the repo. We will be rolling this particular feature out in a heavily rate limited manner. But yeah, it would be good to see this in action in the wild. So in terms of, yeah, again, another subtle issue which you can miss. Now, it is in a lot of cases difficult to detect whether you have IPv4 connectivity or IPv6 connectivity or not, or TCP connectivity or UDP connectivity or not. So you might ask a good peer that, okay, dial me on IPv6 quick. And that peer might be just misconfigured. It may have IPv4 connectivity, but it is misconfigured to have an IPv6 address. The router is providing it, but the router is just dropping all those IPv6 packets. Now, since I have configured myself into such a situation, I believe other people have also. So to provide this service to the network, you need to have an understanding of which of those 4 tuples you are connected on. This is IP, IPv4, IPv6, TCP, or UDP. Yeah. So the good thing is GoLib P2P has already solved this problem. We have a black hole detector which basically keeps track of the dials the node is making, and then keeps track of the sort of 4-tuple connectivity it has, and it will refuse requests for addresses it cannot dial. Other implementations will also need to take care of it. Yeah, so for the status of the implementation, Go implementation is pending PR review. Rust implementation is in progress. In terms of using it, it will take a while. I guess this is another example or a good use case for a peer exchange protocol, because while implementing this out, we will run into the small network problem. Only a few nodes in the network will have AutoNAT2 and you'll not be able to discover any peers. So yeah, we will be having a phased rollout where first we will, or at least we will provide options to first deploy our servers. And when you have sufficient servers on, I think 10% is good enough. Don't quote me on it, but yeah. And then you can roll out the clients which can use the service. Of course, yeah. So these 4 were heavily involved in all the work this was done. The amplification attack prevention is an idea by Martin. Thomas had very valuable inputs, and Max and Marco too.
Could you explain again how like sending the 100 kilobytes of data solves the amplification attack? Like it wasn't really clear.
Yes, in all the cases, client is the one issuing the AutoNAT request. So
I do understand the setup, like in the attack vector itself, but like the solution isn't clear. Like how to.
Yeah. So the thing here is that what is the attack that happens in this case? A client goes out into to a bunch of AutoNAT servers on the network and asks it to dial the target IP. Now, what are the resources spent by the target IP, and what are the resources that would have been spent by the client itself? Okay. So the target node will need to do a lot of TLS handshakes. A TLS handshake consists of 2 components. Basically, you do a lot of keygen, and then you send certificates. Certificates are longish. You would need about, as I said, 10 to 20 KB of data. So the amplification here is primarily that the client is able to, the attacker is able to have the target node spend this bandwidth used in processing the certificates. And that is the attack vector that we would like to mitigate. The reason that I am saying that compute is not as important in this case, the compute that the client would be spending to do the keygen and everything, is because compute the target node would be spending, is because say an attacker wanted to do a TLS flood attack itself. Okay, it can send a lot of TLS requests in parallel, right? So how would it go about doing it? What it would do is it will create the keys required for a TLS handshake once. It will send the key in the client hello with the specific key, specific type of key it is using, and the extensions is want, in this case, nothing. Now the client has spent no compute here. It has only done it once, which is not a lot of compute. But on the other hand, the client will have to process all the data for sending the certificates, right? If the attacker were doing the attack itself, it generates the keys once, so it is not spending a lot of compute, but it is going to send a lot of data, and it is going to receive a lot of data over the TLS handshake. So the cost that the attacker is paying to do the attack itself is that of the data. And if we look at the case of AutoNAT V2, the way it will go about doing this attack is it will ask these bunch of nodes on the network that please dial this. So in this case, it has not spent any compute, but it has also not spent any data, right? It is only sending the addresses of the client, and it has no need to send any bandwidth. Like it is not spending the TLS handshake bandwidth at all. So what we do is we force the attacker to provide data. So now if the attacker goes out to the network and says, okay, dial this guy, dial this guy, dial this guy, it will have to provide this 100 KB of data to every attacker, to every server, which mitigates, which reduces this lucrativeness of this attack system, right? Because when it was doing the attack itself, the cost it had to pay was data. When it is doing the attack by the network, by AutoNAT2, the cost it has to pay is data. And yeah, that's how I think it mitigates it. The reasoning is subtle though. The reasoning around the fact that you don't need much compute is subtle. And it is subtle in the sense that you can use those same keys used in the TLS handshake without spending a lot more compute. There is some compute done to do HKDF over the key material and everything. But the argument is that you can factor that in the large amount of data you want. So a TLS handshake is 10 KB, but you ask for 100 KB, 200 KB to do this. However, yeah, I am open to argument over this. I am not 100% convinced, which is why we are going to roll it out very, and like there will be a lot of options to plug it off. There will be one option to plug it off. But yeah, that is the argument.
So is the main difference between AutoNAT V1 and V2 that V1 is just aware of a peer ID and the granularity of its answers are just a binary one, yes or no, whereas V2 will give you an answer per multi-adder?
Yes, yeah.
Okay.
That helps us be a good network participant, basically, yeah.